Hi everyone. In this video we are going to discuss about the sine law or the sine rule for triangles. Here we will see what the sine rule is and also we will see where it came from, meaning how we can prove it, right? So let's get started. Here in the diagram we have a triangle ABC, and I have denoted the opposite sides of the vertices with the lowercase letters to indicate that the length of the sides are in lowercase letter. For example, the side BC is of the length A units, side AC is of the length B units, and side AB is of the length C units. And similarly, the angles, for example, the angle nearest to the vertex, that angle is named same as the vertex. For example, angle BAC will be called the angle A, angle ABC will be called the angle B, and angle BCA will be called the angle C. Now for this type of a triangle, in this particular example, actually I have taken an acute triangle, but also I will show you how it works for an obtuse triangle as well as a right triangle. But let's start our discussion with an acute triangle like I have on the diagram here. For this type of a triangle, the sine law says that the ratio of A is to sine A. For example, A over sine A will be equal to B over sine B, and that will also be equal to C over sine C, and each of these will be equal to 2 times the circumradius, and that is denoted with an uppercase R. So A over sine A equals B over sine B equals C over sine C equals 2 times R. That is the sine law or sine rule. Sometimes some authors might call it sine rule, some authors might call it sine law, but they both mean the same thing. Now we are going to see where it came from and how it relates to the circumradius. The first thing I am going to do is I am going to drop a perpendicular from vertex A onto the opposite side BC, and let's assume that the perpendicular landed at point D on BC, and that's a perpendicular drawn from the vertex A onto BC. And there are two ways we can establish the relationship. The easiest might be just going by the height of the vertex A. This height is now denoted as lowercase h with a subscript A to indicate that this height indicates the height of the vertex A from the opposite side. So in this case, what would be sine of angle B? That will be equal to opposite over hypotenuse. In this case, opposite is h sub A and hypotenuse is the side AB whose length is C units, lowercase c. And from here, what is the height then? H sub A will be equal to C times sine of B. Similarly, let's find out what would be the sine of C angle. So sine of C angle would be, in this case again, opposite is h sub A over hypotenuse, and hypotenuse is the side AC which is lowercase b units, and from here again if we say h sub A is equal to B times sine of C. Now in both the cases you see we have derived the value of h sub A in terms of a side length and the sine of an angle, right? Now they both will be equal because they both are the values of h sub A. So then from these two we can say that C times sine B will be equal to B times sine C, and then if we divide both sides by sine B times sine C, then we are going to get C over sine C is equal to B over sine B. And similarly, if we drop a perpendicular from the vertex B onto the opposite side AC, then we can establish a relationship with the angle A. So let's try that. Here I have drawn the perpendicular from B onto AC, and let's assume that it landed at point E on AC, and I have denoted that as h sub B. That's the height of the vertex B from the opposite side AC. So here again, what would be the sine of the A angle? That will be opposite over hypotenuse. Opposite would be h sub B over hypotenuse would be the side AB which is lowercase c units, and from here we can say that h sub B is equal to C times sine of A. And similarly, what would be the sine of C angle? That would be opposite side which is h sub B over hypotenuse which is the side BC, and that is actually lowercase a units, and then from here again we can say h sub B is equal to A times sine C, and from these two we can then say that C times sine A definitely equal to A times sine C because they both denote the height which is h sub B. So we can assume that they both are equal, and if we divide both sides by a product of sine A times sine C, we are going to get C over sine C is equal to A over sine A. And now if we look at the two sets of equalities we have in the white boxes here, we can clearly see that each of them is actually equal. So we can say that that A over sine A is equal to C over sine C is equal to B over sine B. Or in other words, we can say A over sine A is equal to B over sine B is equal to C over sine C. So far we have been able to prove that this relationship is true, and now we are going to see how it relates to the circumradius. I hope things are clear up to this point. Now let's talk about the circumcircle. To draw a circumcircle, what we have to do? We have to draw the perpendicular bisectors of each of the sides, and then they would meet at a point, and from that point all the vertices will be at the same distance, and that is how we are going to draw the circumcircle. So let me first draw the perpendicular bisectors of the three sides. Now here I have drawn the perpendicular bisectors of the three sides of this triangle. Let's assume that the three perpendicular bisectors are OD, OE and OF, and they all intersect at the point O, and that point is called the circumcenter, generally denoted by the uppercase letter O. And if that is the circumcenter, then the distance of the vertices from that point would be equal, and let me show that with a dotted line here. So each of these pink dotted lines, they are actually equal and they denote the circumradius. And if I draw the circumcircle, it's kind of going to look like this. So in this diagram, clearly OB equals OC equals OA, and they represent the radius of the circumcircle, which is denoted by uppercase R. Now if we look at the triangle BOC, the angle BOC will be 2 times of A. Now why is that? Well, there is a very important theorem for circle that says that the same chord would subtend twice the angle at the center that it subtends at the circumference on the same side. That means if we have the chord BC of a circle, so BC can be imagined as a chord of this circle, of the circumcircle, and the BC chord is going to subtend double the angle at the center compared to the angle that it subtends on the circumference. Now if you think about it, the angle A, which is way up there at the circumference, that angle is subtended by this chord on the circumference, and then the angle BOC is also the angle subtended by the same chord at the center of this circle. So the angle subtended at the center by this chord will be 2 times the angle subtended on the circumference. So that means angle BOC will be 2 times A. So let me make a quick note here. Now let's look at the two triangles like triangle BOD and triangle ODC. If we look at these two triangles, you see they are obviously right triangles because we have drawn the perpendicular bisector, which is OD. So OD is perpendicular to BC. So both the triangles BOD, let me make a note here, triangle BOD and the triangle ODC. In these two triangles, you see OD is a common side for both the triangles and it is perpendicular to the line BC, and obviously BD is equal to DC is equal to half of A, and also the sides BO and OC, they are also equal because they represent the circumradius, the radius of the circumcircle. So then you can see that for these two triangles, their all three corresponding sides are of equal length. That means the two triangles are congruent triangles. And here I denoted that with the congruent sign. So these two triangles are congruent triangles. That means their corresponding angles will also be equal. That means these angles right here, I am using a yellow arc here. So these angles will be equal. I mean the angle BOD and the angle COD, they will be equal. But their sum is 2 times A. Angle BOC is actually 2 times A. So that means each of these angles will be equal to half of 2 times A. That means they will be equal to A. So essentially these angles are actually equal to the angle A. Now let's calculate the sine ratio of this angle A, which is angle BOD. For example, we can write it as sine of A, and that will be equal to opposite over hypotenuse. In this case, opposite is the side BD over hypotenuse is the side BO, and that is actually equal to half of A over R. So A over 2 over R. So from here we can say that this is equal to A over 2 times R. So then we can say that 2 times R is equal to A over sine A, and that's all we needed to prove. Now we have been able to prove that A over sine A is equal to 2 times R, then clearly B over sine B will also be 2 times R, and C over sine C will also be equal to 2 times R. So we have proved that each of these ratios, the A over sine A or B over sine B or C over sine C, each of them is actually equal to 2 times the circumradius. So let me make a note there. Within the green box, I have made a note that each of those ratios is actually equal to 2 times r. I hope things are clear up to this point. Now let's try the same thing on an obtuse triangle. Here in the diagram, I have an obtuse triangle where side AB is equal to C, side BC is equal to A, side AC is equal to B units, and similarly we have the angle BAC which is equal to A, uppercase A of course, and then angle ABC equals B and angle BCA equals C degree. And here the angle A is the obtuse angle and I have denoted that as being greater than 90 degree. Now for this triangle, let's see if we can establish the same relationship for the sine rule. So the first thing I'm going to do is I'm going to drop a perpendicular from the vertex A onto the opposite side BC, and let me do that. And let's assume that the perpendicular landed at point D on the side BC, and let's denote this perpendicular, the height of the vertex A from the side BC, as h sub A to indicate that it's the height of the vertex A from the opposite side. So here what would be the sine of B angle? That will be equal to opposite side, which is h sub A, over the hypotenuse, which is actually the side AB, and that is lowercase c units. So we can write it like this. And from here what would be h sub A? That will be equal to c times sine of B. And similarly what would be sine of C angle? That will be equal to opposite side, which is again h sub A, over the hypotenuse, which is the side AC, and that is actually lowercase b units. So we can write it like this. And from here we can say then h sub A is also equal to B times sine of C. And from here then we can clearly see that C times sine of B and B times sine of C, they both represent the height h sub A. So that means those two quantities are equal. And if we divide both sides by a product of sine of B and sine of C, we are going to get C over sine C is equal to B over sine B. Next, I am going to try and drop a perpendicular from the vertex C onto AB. Well, we actually have to extend the side AB to draw this perpendicular. So I am going to extend the side BA to some extent, and then we will drop the perpendicular from C onto the extended portion. So here I have extended the side BA. Now let me drop the perpendicular from C, and let's assume that the perpendicular landed on the extended BA side at point F, and we can denote this height as h sub C to denote that this is the height of the vertex C from the side AB. And now let's think about the angle CAF. Now what would be angle CAF? That is clearly 180 degree minus A. We can write it as pi minus A, because you see the angle A is right there. This is the angle A right here. So then the supplementary angle would be 180 degree minus A or pi minus A. So angle CAF is actually pi minus A. Now let's do the sine of this angle CAF. We can write it as sine of pi minus A, and sine of pi minus any angle is equal to the sine of that angle. So this is nothing but sine of A, and this is equal to opposite over hypotenuse. Now what is opposite? Opposite is actually h sub C, and hypotenuse is actually the side AC, which is lowercase b units. So from here we can say that h sub C is equal to B times sine of A, and let's also do the sine of B angle. That will be equal to opposite side, which is h sub C, over the hypotenuse, which is the side BC, and that is equal to lowercase a units. And from here we can say that h sub C is equal to A times sine B. So from these two relationships we can say that B times sine of A is equal to A times sine of B, because both of them represent h sub C. So we can say that B times sine of A is equal to A times sine of B, and if we divide both sides by a product of sine of A and sine of B, then we are going to get B over sine of B is equal to A over sine of A. So now if you look at these two relationships, we can clearly see that A over sine of A is going to be equal to B over sine of B, and that is again going to be equal to C over sine of C, and I have made a note of that in the green box here. Now let's try to see how this relates to the circumradius for this particular obtuse triangle. Let me erase the details on the left hand side. Here let us draw the diameter through the center of the circle from the vertex B, and then let's join the points C and D. And now if you think of the angle BCD, that's nothing but a right angle. Why? Because the diameter of a circle always subtends a 90-degree angle on the circumference. We know that from the theorem of circles. So this is going to be a right angle right here, angle BCD. And now if you look at the quadrilateral ABCD, BD, that's a cyclic quadrilateral, and the sum of the opposite angles of a cyclic quadrilateral is always equal to 180 degree. That is also another theorem of circles. So in this case, the sum of the angle A and angle D, that will be 180 degree. So this angle D right here, the angle BDC, will be equal to 180 degree minus A, or we can write it as pi minus A. So here clearly BD is equal to 2 times the radius, meaning that's the diameter, which is equal to 2 times the radius of the circumcircle. Now if we do a sine of the angle BDC, that is equal to sine of the angle pi minus A, and we can clearly write it as sine of A, because sine of pi minus any angle is equal to the sine of that angle, and this is actually equal to the opposite side, which is side A, over hypotenuse, which is 2r. The opposite side of this angle is actually the side BC, and that is actually lowercase a units, and then hypotenuse is actually BD, which is the diameter of the circumcircle, and that is actually 2 times the radius. So then from here we can clearly see that 2r is equal to A over sine A. So A over sine A has been proved to be equal to 2 times r. Then obviously B over sine B will also be equal to 2 times r, and C over sine C will also be equal to 2 times r, because we have already proved that relationship, right? So then finally we see that all these ratios, A over sine A, B over sine B, C over sine C, each of them will be equal to 2 times r. So let me make a note of that, and I noted it inside the green box to indicate that each of those ratios is also equal to 2 times the circumradius. I hope things are clear up to this point. Next, we are going to prove the same thing on a right triangle. So far we have proved it for an acute triangle and an obtuse triangle. Next, we are going to prove it for a right triangle. Let's suppose we have a right triangle ABC as in the diagram. Side AB is equal to lowercase c units, side BC is equal to A units, and side AC is equal to B units. And similarly, the angle BAC, which is the angle A, and that is 90 degree, because it's a right triangle, I have made it as 90 degree. And then angle ABC will be called the angle B, and angle BCA will be called the angle C. So here again we are going to prove the same relationship. So the first thing I am going to do is I am going to drop a perpendicular from the vertex A onto the opposite side BC, and let's assume that the perpendicular landed at point D on the side BC, and let's denote this height of the vertex A as h sub A. Now one very interesting thing that we need to notice is that angle BAD will be equal to angle C. That's a very interesting property of right triangle, that when we drop a perpendicular onto hypotenuse from the opposite vertex, then it divides the angle into the two other angles. Because in the original triangle, angle B and angle C equates to 90 degree together. So B plus C is 90 degree. And here again, if you look at this right triangle, which is triangle ABD, there also clearly this will be equal to angle C. I am denoting that with a yellow arc there, so that will be equal to angle C. And similarly, the angle CAD, that will be equal to angle B. So this angle right here, that will be equal to angle B, because B plus C is 90 degrees. So if you look at the right triangle ADC, there again we already have a 90 degree angle, which is angle ADC, and then we are left with the angle C and this other new angle, so that must be equal to B. So from here, let's take a few sine ratios. So first, we are going to take the sine ratio of the angle B, and that will be equal to opposite side, which is h sub A, over the hypotenuse, which is the side AB, and that is actually lowercase c. And from here we can say then h sub A is equal to C times sine of B. Similarly, let's take a sine ratio of the angle C, and that will be equal to the opposite side, which is h sub A, over the side AC, which is lowercase b. And from here again we can say h sub A is equal to B times sine of C, and from these two relationships we can see that C times sine of B will be equal to B times sine of C. And if we divide both sides by a product of sine B and sine C, we are going to get C over sine C is equal to B over sine B. Now let's also look at the original triangle, and let's calculate the sine of B. Sine of B from the original triangle will be equal to the opposite side, which is AC, and that is lowercase b, over the hypotenuse, which is BC, that is lowercase a. And from here, can we write it as A equals B over sine of B, and then from here can we write that a as a over 1 is equal to b over sine of b, and then can we write a over 1 as a over sine of 90 degree is equal to b over sine of b, and now clearly you can see that we can write it as a over sine of a because the angle a is a 90 degree angle here in this particular right triangle. So you can write it as a over sine of a is equal to b over sine of b. Now if we look at these two relationships here, we can clearly see that a over sine of a is equal to b over sine of b is equal to c over sine of c. So we can say a over sine of a equals b over sine of b equals c over sine of c, and then we are going to establish the relationship with the circumradius. Now for that we have to draw the perpendicular bisectors of the sides. Here I have drawn the perpendicular bisectors of the sides AB and AC, and actually these bisectors would meet at the midpoint of the hypotenuse. That's a very interesting theorem of right triangle, where the perpendicular bisectors of the two sides, they meet at the midpoint of the hypotenuse. Since these are perpendicular bisectors, in this particular diagram you can see that OD will be perpendicular to the side AC, and similarly OE will be perpendicular to the side AB. So then clearly AB will be parallel to OD, or rather OD will be parallel to AB, and using the midpoint theorem of triangle we can clearly see that OD will also divide BC in the equal ratio, and that equal ratio is actually 1:1 because D is the midpoint of AC. Similarly, O will be the midpoint of BC. The perpendicular bisectors of the two other sides, they will meet at the midpoint on BC. So now let's draw the circle. And the circle going to look like this, where BC will be the diameter, O being the circumcenter, and OB will be equal to OC, and each of them will be equal to R. And now if we take the sine ratio of the B angle, so we can say sine of B equals, it will be opposite side which is lowercase b over hypotenuse which is the side BC, and that is actually equal to 2R. That's the diameter of the circumcircle, right? So from here we can then say that 2R is equal to b over sine b, and we have already proved it. So b over sine b is equal to 2R, and previously we have proved that b over sine b is equal to a over sine a is also equal to c over sine c. So each of those ratios would be equal to 2R, which is the diameter of the circumcircle, and I have noted it inside the green box. So there finally we see that we have been able to prove that each of these ratios, a over sine a, b over sine b, c over sine c, each of these ratios is also equal to the diameter of the circumcircle, which is 2 times r. And we have been able to prove it for all types of triangles: acute triangle, obtuse triangle, and right triangle. And we have been able to prove that each of these ratios would be equal to 2 times r, r being the radius of the circumcircle. Hope everything made sense. Thank you for watching. See you in the next video.